All right. So now we're going to start with a new topic on multi-relational graph neural networks. So far in the previous lecture, we discussed about extracting essentially embeddings, learning embeddings for knowledge graphs, multi-relational graphs, using shallow embedding approaches. And we said that before, shallow embedding approaches are basically, they have 4 elements. They're an encoder, decoder type of framework that needs encoder, a decoder, a similarity measure, and a loss function, right? In order to train and learn different, basically, knowledge graph embeddings, or in general, multi-relational graph embeddings. So in the previous session, we went over a number of decoders, but we used shallow embedding, right? So that means that we don't have encoder. Then now we can enrich this model if we introduce some encoder, right? So we can introduce some encoder that basically, instead of just having a dictionary lookup, we can actually have an encoder. But so far, what we have studied on graph neural networks, they have been propagation rules that are based on neural message passing over nodes, right? So we're just looking over node embeddings, and we're aggregating information from our neighborhood, and we're updating and so on and so forth. So what we want to do in order to be able to deal with multi-relational graphs is to introduce basically, or generalize these to account for the edge relations. So essentially edge types, edge embeddings, or edge features, whatever basically we want to call them. So just a review on what one of these models was doing, graph convolutional network. What we were doing in order to define our propagation rule was to first we aggregate information from a neighborhood of the node using a summation, for instance, some basically function set pooling. Let's say that now we are using summation. And for instance, we can normalize that as well, which GCM was doing, using the square root of the degrees of the 2 nodes, the node itself and its neighbor, right? So we do that, we normalize that. In the update stage, then we take that, we update that using some learnable parameter, and then we apply some nonlinearity, and we get the output for essentially that node's embedding in the next iteration. So now we define our weight as a dk by dk minus 1 dimensional matrix, where dk refers to dimensionality of the embedding, node embeddings at stage k. dk minus 1 refers to dimensionality of the essentially node embeddings at step k minus 1. So the inputs are vectors of size dk minus 1, and outputs are vectors of size dk. And now we said that we were using this as our weight matrix, our model parameter. But note that we're using essentially the same thing to update all embeddings on different neighborhoods, right? So in multi-relational graph, this causes an issue because it is not considering the fact that it is receiving these information from neighbors through different channels, through different type of relations, right? So we need to somehow account for the information that comes from the neighbor being through a different type of edge. So for that, we are defining relational GCNs. So in relational GCNs, what we do is that we take the parameter W that we have inside the summation, and then we define a essentially relation specific weight for each type of relation that we can have. So if node, essentially, if the embedding HG is coming through a node of type tau, I will use W tau for that. If it's coming from W tau 2, I'm using another W. So I multiply the embeddings I basically update them through different learning parameters. And that's essentially the essence of relational GCNs. So I have a summation here over all the nodes of neighboring nodes and the node itself. And I have a second summation here over all the edge types. And I include a tau 0 here as well, which means that it is the self-loop type of relation. So we introduce self-loops because we want to basically our embedding at level k be informed of the embedding of the node at the step k-1. So that's basically also included in our different types of the relations that we have. So self-loop we added. All right, so we can take a look at this diagram to see how it works. So let's say that I have this directed graph, and let's say that this is multi-relational. That means that there are different relations that connect different nodes here. And now let's say that I want to update embedding for node 3. So I'm here showing different type of embeddings using different colors. And I say that for node 3, I have two type of information that are coming or basically going out. I have types that I'm showing with green. I have types that I'm showing with orange. And the node itself, I'm showing with magenta. Now, so I can divide this into 3 groups, right? 3 groups of relations, 3 type of relations that it has, plus the self-loop type, right? But note that the relations here are of 2 kinds. There's ingoing information and outgoing information. So for each of these, again, relational GCNs define a different type of weight. So I separate this basically. So this is the whole set of different informations that we gathered. Outgoing information of type green, incoming information of type green, outgoing information of type orange, so on and so forth, and the self-loop, right? So I have essentially 5 type of relations here. So it's tau, the total number of relations, times 2, because it is incoming and outgoing, plus the self-loop, so 2 tau plus 1. Now I want to basically update my information on node 3. And what I do is that I essentially multiply the sum of each of these separately to a separate relation-specific basically weight parameter. So now there's a problem with this approach. And the problem is that let's say that we want to deal with a knowledge graph, which has hundreds of thousands of relationships. That means that in the previous, like in GCNs, we had in the first layer, we had some weight W that we were sharing throughout the graph, right? But now I have hundreds of thousands of different weights that are that are specific to different relation types that I need to handle. And then, it can be very expensive. It can, in basically examples like a knowledge graph, it can be very expensive and you can't handle that. So you want to come up with some approach to handle this type of basically problems. For that, we have 2 approaches. We have basis decomposition approach, where we decompose our relational weights into some basis, and then we have some sharing there. And the second part of the thing that we can use is some sort of sparsification of these weight matrices. So we do that through block diagonal decomposition. So first thing first, let's go over basis decomposition approach. In this approach, as I said before, as basically you can see from the name, we decompose the weight into some basis V. So let's say that we have some basis matrices V for each basically type. We write the W as decomposition into these basis matrices. And I say, for instance, I have B of these. So I'm summing over 1 to B, and there is this alpha, which is some coefficient for summing these up. So I have VW, which has dimension dk times dk plus 1. I have vk, which has the same dimensionality, and I have A, which is just a coefficient. And I have a vector of these coefficients for computing each W. So now, in order to reduce the number of parameters that we deal with, what we do is to share these bases. So I define, instead of having hundreds of thousands of matrices, I define 100 matrices, and these are shared across all different weight types. And I decompose my weight types in these bases. So when I do that now, I'm left with 100, for instance, B, essentially capital B matrices, V, and then I'm left with a coefficient, a vector for each edge type, right? So I reduced the number of parameters that I basically have specific to each relation to a vector of dimension B. Right? So instead of having hundreds of thousands of W's, I have hundreds of thousands of basically 100-dimensional vectors, not even D by D, right? So, and that can be, 100, just as an example, it can be lower than that. Just anything that, gives a good performance. The second approach that we can take is just using block diagonal essentially representation in order to present our relation-specific weight in a sparse way. So the way to do that is using a concept called direct sum. So direct sum of two essentially matrices, dense matrices, is a new matrix, block diagonal matrix, which has these dense matrices on its diagonal, right? So I have V1 directed sum with V2. I have a matrix which has V1 and V2 on its diagonals and 0 everywhere else. That way, what happens is that I will have a sparse output matrix, right? So I can use this concept and define my WT just using a number, again, let's say B, essentially dense matrices, which are of smaller dimensions. So if you write down, I show the basically our relation-specific W as a sum over these essentially smaller matrices, which have, let's say that I have B of these, so I divide the dimensions of W by B, and then I will have, let's say that dk over B times dk plus 1 over B dimensional matrix, and I have B of these. So that's the way to define a sparse, essentially, weight matrix and reduce the number of total parameters that we have. Go ahead.
Yeah, for the first method, they can do relation using bases.
Okay.
How do you find them?
Oh, learnable. So you have two sets. So you have learnable shared matrices V, and you have learnable parameter-specific vectors A. So yeah. So although these are still basically there, you need to learn them, but they're very smaller than the total number of relations that you have. And although you have vectors A that you're learning for W, there again, very few of them. So and they're vector, they're not matrices. So it is way cheaper.
Wait, so you're saying the VB is also learnable?
VB, yes. So VB is learnable, but is shared across all of them. AB is specific to each relation type.
But VB, for example, VB is learnable, meaning that every element inside VB is learnable.
Yes.
Then it should be as the same dimension as W.
Yes, that's true.
So how did you reduce the dimension?
So how many, all right, let me ask you, how many W's that we have?
For every tall, for
Yes.
every,
How many can we have? How many relation types we can have in a graph? Very large number, right?
yeah,
So we can have hundreds of thousands of different relations in world, right? Every type of relation in the world you imagine, someone being son of someone, parent of someone, everything. But how many B's you have now?
you can set it by yourself.
Exactly, I can set it by myself.
You're like, hey, I have like 1,000 type, but I don't want to train 1,000 W. Just choose 10
Mhm,
and some parameters.
mhm.
That's
Exactly.
some coefficients, sorry.
Some coefficients.
Yeah, that's
Exactly. So you have hundreds, for example, you have 10, yes. So you have reduced your 1,000 matrices into, let's say, 10 matrices, okay? But you have added computation that you need to learn vectors, a 10-dimensional vector for each relation type. But, you know, that's what, 1,000 by 10. Plus, you know, you can do the math and it's always basically, you can do it way cheaper than directly learning weights.
about the second one. So if you put the matrix in those block diagonal, it means that when you multiply the vector, you're dividing the vector dimension to subspace, which are decoupled.
Yes.
So I think the first method is more general, makes more sense.
Yeah, I see what, that's the point that I'm going to make. You're talking about the communication between different dimensions of, yeah, that's true. And you should have, for instance, you should have, you can use some method that to essentially alleviate that. For instance, you can have multiple iterations that have different sizes of blocks.
Okay.
So that basically they overlap. But yeah. So, but I'm gonna repeat that again. All right. So, but there is one drawback with the block diagonal decomposition, and that's the fact that when I have dense matrices on the diagonal, that means that the dimensions of the embedding that fall into each of those blocks communicate more tightly with each other. And what happens that is that communication across those blocks is minimal. So we can use different approaches. For instance, we can take care of that in different iterations and using a different size of basically dense blocks in the next iteration, or some approach of that sort in order to essentially remedy this. So a second problem is, not a second problem. A second approach is proposed. All right, let me just restart. However, sometimes in basically the relational GCNs that we study, we consider that we have different types of edges, right? Type 1, type 2, type 3. So it means that I assume that these types are discrete. I can show them using a set of different types, right? But what if these are real values, for instance? It's not falling into any categories, or let's say that these are just vectors, real valued vectors, right? So these are not categories this time, these are real valued vectors. Now, how do you go and define a essentially relation specific weight for different real values on edges? It is not easy. We won't be able, and we should be essentially define a new weight for every edge, right? So what we can do is using some embedding concatenation. And let's say that now I have these vectors defined on these edges, and I want to essentially handle this graph using some multi-relational GNN. The way to do that is not by defining weights specific to each relation, but concatenating these embeddings with the embedding of the node. So that means that, let's say that each of these, I'm showing just different real value, let's say, with a different color. You see that different edges have different relations, right? Different colors. Every one of them is unique to itself. So what I do now is that I concatenate the embedding of this node with the embedding vector of the edge that connects it to the node that I'm aggregating information for, right? So let's say that it's a three-dimensional vector, d-dimensional embedding vector on 2. I concatenate that with the real valued vector that I have here. I get a new vector, and when I aggregate information for node 3, I aggregate all those, right? So essentially, the only constraint that this model has is that we should have the same dimensionality for the embeddings throughout the graph for different edges and different nodes, which is, usually defined that way, right? Because we usually collect the same type of information for all the edges. Now we can write that, for instance, as concatenation of, let's say that I define HI to be my k-dimensional real valued vector for node embeddings for node VI. And then I define a d prime dimensional real valued vector Hij for the embedding of the vector of the essentially edge that connects nodes Vi and Vj together. So then I concatenate those two together, I get a new vector, and I use some aggregation approach, let's say, for instance, summation or maximization of element-wise maximization or so on and so forth, in order to construct my message. All right,